We discussed synchronization, load imbalance, and resource contention. And if you look at this, the difficulty in parallel programming arises because of these three bottlenecks. There's little difficulty in parallel programming if parallelism is natural. For embarrassingly parallel applications, it's easy, right? Many multimedia, physical simulation, graphics applications, it's relatively easy. And perhaps large web servers and databases, it's not as easy, but it's still easier. But the difficulty is in two things. One is getting parallel programs to work correctly, and the second is optimizing performance in the presence of these bottlenecks. And these are very tightly related. If you don't need to optimize for performance, getting parallel programs to work correctly is actually easy, because you have reduced the parallelism in the program, right? But if you want to optimize for performance, then you would like to maximize the parallelism, which means that you would like to minimize these bottlenecks. And that minimization of bottlenecks lead to bugs, because now the programmer needs to reduce the size of the critical sections, for example. Devise more sophisticated dynamic tasking schemes. Devise more sophisticated queues. Devise more sophisticated mechanisms for locking those queues. Now, if you make a simple mistake in any of those steps, then your program becomes incorrect, because you're optimizing for performance, right? Because these two things are very tightly coupled. So much of parallel computer architecture and much of multi-core design today is about designing machines that overcome the sequential and parallel bottlenecks to achieve higher performance and efficiency, and also making the programmer's job easier in writing correct and high-performance parallel programs. Now, that may not have been the approach when industry moved to multi-core, because they really didn't think of the programmer, perhaps. But I would argue that this needs to be the approach if we would like to scale the systems going forward to multi-core.
By the way, you do not think of I/O bottleneck. Am I wrong?
So I/O bottleneck, I agree, that's also a bottleneck. But I would categorize this as part of the resource contention, because it's another resource, just like memory, just like interconnect, that's shared across many different cores. And if you have too many cores sharing the I/O, then now you have an I/O bottleneck also. Okay, there are two multiprocessor types. We'll be focusing on the tightly coupled multiprocessors in general. Loosely coupled means no shared global memory address space. And tightly coupled means shared global memory address space. Although they're actually similar fundamentally at some level, they're different in the sense that you need to maintain this shared global memory address space here. This is the same thing as a multi-computer network or network-based multiprocessors, right? You program them usually using message passing. And this is different. This is traditional multiprocessing, or it's also called symmetric multiprocessing. Existing multi-core processors and multi-thread processors are this way. These are usually programmed via message passing, not always. They don't have to be. In fact, you can implement a shared memory implementation on top of a network, but that tends to have overheads. So you can have explicit calls, send and receive for communication. This is a distributed system, basically, right? Today, distributed systems are programmed using remote procedure calls, for example. Tightly coupled multiprocessors usually programmed similarly to uniprocessors, and that's one of the beauties of shared memory programming paradigm, right? You can do load and store without thinking about send and receive. You just need to think about synchronization. Basically, yeah, that's operations on shared data require synchronization. That's the major difference here. And you could argue that which model is better in terms of performance, and people have thought about it a lot. But we'll look at some of the mechanisms, like explicit send and call mechanisms, integrated into tightly coupled multiprocessors today. So maybe the best of both worlds is somewhere in between. And I've actually talked about the many things here. One is the hardware design, which is shared, or what is exposed to the programmer, shared global memory address space, or no shared global memory address space. You can actually make these trade-offs at different levels: hardware, software, what is exposed to the programmer and what's not exposed to the programmer. You can actually design, the hardware can be loosely coupled, but the programming model may be shared memory. The hardware can be tightly coupled, but the programming model can be message passing. You can actually mix and match all of these different things. We'll not go into those details, but we're going to assume that the programmer sees a shared global memory address space. Okay, let's go into multi-core processors, which are basically examples of these tightly coupled multiprocessors today. Why have we gone to multi-core? You've probably seen this chart, and this is another seminal paper. How many people have read this paper? We all talk about Moore's law, right? This is only a 4-page paper, I think, or 3-page paper. But he wrote in 1968. And this is, again, a beautiful paper. It's not a law. It's just an empirical observation, right? He basically plotted this graph in 1968, around here. And he saw the same exponential increase in the number of devices that you can fabricate on a circuit, which we call transistors today. And basically, we're having more and more transistors, and this is continuing still, as this chart shows, stolen from Wikipedia. And this ends in 2011. And these are basically Intel processors, I believe, or x86 processors. And they have this nice curve. You basically, the number of transistors has been increasing exponentially over years. And that begs the question, what do we do with these transistors, right? And at some point, the industry decided that they will go with this idea, put multiple processors on the same die, because they ran out of other options potentially, which we're going to examine. Basically, technology scaling enables these transistors. One option is to put multiple processors on the same die, as industry did. But there are many other options. Why did they not go that way? Let's discuss this a little bit so that we can think about perhaps better ways of designing a system. You can have a bigger, more powerful core. You can have larger caches in the memory hierarchy. You can have simultaneous multi-threading. You can integrate other platform components on chip. Now, these are not necessarily orthogonal to each other. You can do all of them at the same time, right, to actually use these transistors. And some of that is happening. But the predominant trend was to put actually multiple processors on the same chip, instead of doing, for example, this bigger, more powerful core. And let's talk about some of the trade-offs compared to putting multiple processors on the same die. So one multi-core alternative is actually having a bigger, more powerful single core. You have a single-threaded engine, and you can increase the number of instructions you can fetch per cycle, the number of instructions you can issue per cycle, execute per cycle, retire per cycle. Now, this has been around 4 to 8 in industry, but you can make it 128. You can issue 128 instructions per cycle, right? You can increase the size of the instruction window. And instruction window, I've already told you, this is the buffers that keep the instructions that are decoded but not yet retired from the processor. In a von Neumann processor, you need to retire instructions in sequential order. And if you want to execute instructions out of order, the processors work by buffering the instructions and figuring out which instructions are independent. Now, we can go into detail of that, but that would be another lecture. But it turns out increasing the size of this makes it a lot harder to search for independent instructions. Because whenever this load becomes ready, it needs to notify all of its dependents, your data is ready. And how do you do that? Well, basically, this load broadcasts a tag associated with its data value. And this tag is compared to every single instruction in the instruction window. And that comparison is essentially content addressable memory. And as you increase the size of the instruction window, you're increasing the size of the comparators. You're increasing the number of comparisons. You're also increasing the size of the comparators because your tags need to increase. There's so many instructions that can broadcast, right? So the complexity grows quadratically with the number of instructions because of this reason. Now you can imagine that alternative is quickly becoming not a great alternative because it's becoming expensive, right? Now you can add more execution units, you can add larger caches, larger branch predictors, because as you increase the size of the instruction window, you want to have a better branch predictor as well, because let's say you have 1,000 instructions in the machine. By the way, for comparison, today's machines have about 128 to 192 instructions in their window. I believe Intel's Haswell has 192 instructions in its instruction window, which is large compared to today. But if you have a load instruction that takes 500 cycles, and if you're actually fetching 4 instructions per cycle, in order for the machine not to stall, you really need a 2,000 entry instruction window, right? 500 times 4. Now that's very large. And if you want to make it large, one problem is the branch problem. If you actually have a branch, normally today's processors predict the branches so that they know what instructions to fetch because they have long pipelines. Now, if one branch is mispredicted, you flush your entire window, which is, let's say, 2,000 instructions. Now, you wasted a lot of work. You reduce your energy efficiency. So you need a better branch predictor to support a large instruction window also. Otherwise, you'd be flushing your window very frequently. So all of these need to be done at the same time almost to get a bigger, more powerful core. And there's a big upside to this. You can improve single-thread performance transparently to the compiler and the programmer. And this has been the way the industry worked for a long time, right? Hardware designers provided these bigger, more powerful, high-frequency single cores that executed single-thread programs fast. Software industry like Microsoft built applications that took advantage of this. They added much more clutter or features into their applications such that they can take advantage of it. The software became slower, and we went into this vicious cycle, if you will, where the hardware became faster, software became more complex and slower, and software designers did not need to worry about anything. So that's beautiful. We could continue the cycle if we do this. So there's a lot of incentive to do this. And people yet did not do this, right? They did not go to bigger, more powerful cores, and that's part of the problem we're seeing. The reasons are many. First of all, this is very difficult to design. It turns out scalable algorithms for improving single-thread performance, doing this search, content addressable search, became elusive, became difficult to figure out. I'll talk about some examples. This was actually part of the, this was actually the problem I targeted in my PhD thesis, and I'll give some ideas on what those were. How do you design this window without actually designing it? How do you get away with a small window? Basically, that was the idea. But if you would like to get the most performance, you would like a large window. And it becomes power hungry also because this content addressable search consumes significant power and area. You also need a larger register file, right, to communicate values. You also need many more bypass paths if you want to support more instructions. And you also get diminishing returns on performance. If you increase the size of your window, size of your width of your instruction, how many instructions you fetch, you get diminishing returns. Because you cannot optimize all of these things at the same time. It becomes very difficult. And finally, it turns out this doesn't significantly help memory-bound application performance unless you actually make the machine really large. Because memory latency today is one of the dominant factors in processing. It takes 500 cycles as an example. Xbox, for example, had 650 cycle memory latency. And many other processors have latencies on the order of 100 nanoseconds. So if you want to design 10 gigahertz processor, you're already at 1,000 cycles, right? And if you want to tolerate 1,000 cycle latency, then your window needs to be huge. So a lot of these techniques do not significantly improve the performance of an application that keeps going to memory. There are better, simpler techniques, as we will see. And these are actually the reasons this alternative has been dismissed by the industry, mostly. But we may be going back to it. Okay. So this is a paper. This is Kunle Olukotun's paper. This is actually one of the first papers that introduced the idea or evaluated the idea of multi-core, the case for a single-chip multiprocessor. What they did was they took area equivalent two types of processors. One is a large superscalar processor. Basically, it has a lot of these things that I've discussed here. And the other is simple 4 processors. If you look at this, I think these were simple dual-issue in-order cores. And they compare the performance of these two things. And they found out that this actually performs better in many applications. And I'll discuss why. But let's take a look at the advantages and disadvantages of these two approaches. One is a large superscalar. I will call that superscalar out-of-order execution machine. It has all these bells and whistles of a machine that can execute a single thread much faster. And I'm not going to go into this detail. I'm assuming that you've seen some of the out-of-order execution work in your classes. Yes? Okay, looks like I see a lot of nods. And this is basically 4 processors in this case. The advantages of multi-cores, now you can have simpler cores, right? More power efficient, lower complexity, easier to design and replicate. And you can make them higher frequency also if you wish, because it's easier to do so. Whereas it's harder to do so when you need to do this huge content addressable memory. Because you can have shorter wires and smaller structures. You get higher system throughput on multi-program workloads. If you are running multiple workloads, now you have higher system throughput. Very likely because you have reduced context switches. You get rid of some of the software overhead. And you also get higher system throughput in parallel applications. Very likely. The disadvantage is this requires some parallel tasks and threads to improve performance. Now the problem is punted upon the programmer. A little bit at least. Unless you already have these tasks, right? Resource sharing can reduce single-thread performance, as we've discussed. And you have shared hardware resources that need to be managed somehow. And we'll look at that. So when Kunle and his students wrote the paper, they talk about 2 things, which are usually true when you actually design, when you actually have a paradigm shift in the design of computers. One is a push of the technology. which is this technology was limited at the time. Basically, the idea is you have these instruction issue queue, this CAM, content addressable memory, that limits the cycle time of this processor, single-threaded processor. It leads to diminishing performance returns. And it leads to a quadratic increase in complexity with issue width, as we discussed, and the window size also. And also, the second reason was you need to have a large multi-ported register file if you want to design a wide superscalar processor. Let's say you're fetching 8 instructions per cycle. Each instruction sources 2 registers. Now you need a 16-ported register file, right? And this reduces the frequency, and it leads to lower, well, it either reduces the frequency or leads to multiple cycle access of the register file, and leads to diminishing performance. So this technology push was pushing towards multi-core, making this a more attractive alternative, this one. And also there was the application pull, which is potentially true at the time. Integer applications, they found that there was little parallelism, which is arguable, actually. Floating point applications, they found that these could be easily parallelized because there's an abundant loop level parallelism. And they also looked at other applications like transaction processing and multi-programming. They found that these are multi-core or chip multiprocessing. CMP is a better fit for those applications. Now we could argue with all of those, but if you look at the general trend, it's true that you can partition a program if you put some effort that can execute much better in a 4-core system potentially compared to a single core system. The application space may be larger if you put the effort of the programmer, right? There's that big if over there. So that's one alternative. And there are 2 major reasons for the technology shift. One is the push from technology, the second is the pull from the application. And this is probably true all the time in computer architecture. The key question is, when do you actually do the switch? The second alternative, which is not necessarily an alternative, which is not necessarily orthogonal, is bigger caches. But to think of this in the right perspective, do you actually add more cores or add more cache to your processor? And people have opted for both today, but multi-core has prevailed for a while. The advantage of caches, bigger caches, it improves single-thread performance transparently again to the compiler and programmer, right? The programmer and compiler doesn't need to do anything. Now they can be designed much more interestingly and much more intelligently to take advantage of the cache. That's an additional thing to do, but even without that, if you have locality in your programs, this improves. And it's simple to design also. Caches are actually very easy to add. You can add another level of cache, and that's what's been happening before multi-core. And I'll give you a cartoon of that. The downside is this is not a great alternative because you have diminishing single-thread performance returns from the cache size. Because actually, if you have a streaming application, caching is useless, right? You can never cache it. If you do not have good locality, temporal or spatial, caching is useless. And most applications have these diminishing returns. Locality is not perfect in applications. And there's complexity added to this also. Multiple levels complicate the memory hierarchy because you cannot design a perfect cache that is low latency and large at the same time, high capacity. So you need to have multiple levels. Now you need to manage those multiple levels, and this complicates the hierarchy. So I have this picture of why people have moved to multi-core. People have been actually adding bigger and bigger caches over time. If you look at time of the design of multiprocessors, you can think of initially when microprocessors were designed, there was no cache on chip. Right? Initially we had microprocessors and caches outside the chip. And not even caches, even before some point, before Morris Wilks thought about caches the first time. And over time, people decided to add a little bit of cache, and the cache kept increasing. And eventually, processor became bigger, but caches became even bigger. And at some point, it became so embarrassing that the computer architects decided that we shouldn't be adding more caches, we should be adding more cores so that it's less embarrassing. Because you designed the system to actually do processing, right? Processing is really done in the processor itself, microprocessor. But if you keep adding caches, you're not doing processing. Okay, this is just a cartoon. It's not real, but there may be some truth to that, right? People need to keep their jobs, and it's not clear if by adding a cache then you can become a cache designer rather than a processor designer. But this is still true, this breakdown. Most of the processors actually left to cache because that's one of the major bottlenecks, right? The memory system itself, especially with data-intensive applications, is a big bottleneck, yes?
For the pros and cons, we said simple design design, and then we said it is complicated hierarchy. So I couldn't get
That's right.
regarding the design, which part will be simpler and
So the cache itself is very simple to design, right? You can design a cache and you can put it on chip. But the management of it, adding more levels, is harder, right? Now, nothing is as simple as it looks. Even multi-core will be harder, right? It looks simple. Stamping out the cores is very easy. The problem is managing the resources around them. That becomes harder. It's very similar here. Stamping out the cache is very easy because it's very banked, regular structure. But management part of it is the hard part. Okay. Okay. So there are other alternatives to multi-core which get some of the benefits of multi-core. One is multi-threading, having more threads on the same chip. You still design a large core, big core, but have more threads use the execution units. And there have been many forms of multi-threading. Simultaneous is one. Simultaneous specifically refers to the fact that you can execute from multiple threads in the same cycle. You can basically decide to issue from different threads to different execution units in the same cycle. There have been other multi-threading approaches like fine-grained multi-threading where you switch cycle by cycle to a different thread, but you don't issue from the same thread, different threads in the same cycle. The upside is this exploits thread-level parallelism, just like multi-core. It achieves a lot of the benefits of multi-core, right? You can have many threads at the same time. You can also have single-thread performance because you still have a large core. Right? You get good single-thread performance. You don't need to have an entire core for another thread. You can even have much finer grained communication. If you want to parallelize your program and the task communicate very quickly, in very fine grain, you can do that communication at the L1 cache level, right? Because these threads share the L1 cache. So there are a lot of upsides to this. The downside of this approach is the scalability. Normally I would ask you what the downside is, but we don't have a whole lot of time, but the downside is scalability. How far can you scale this approach? Because as you add more threads on the same chip, you need to have bigger register files, a larger issue width. And this becomes complex with many threads. Or you need to have many execution units. Now you can get rid of some of these by clustering. You can say this thread has this portion of the pipeline, and this thread has this portion, this thread has this portion. Now you're becoming more like multi-core now, right? Because you're partitioning your pipeline. Whereas simultaneous multi-threading is all about sharing the pipeline. So the downside is scalability. It turns out people have shown that this scales up to 4 threads and maybe 8 threads in a single core. But if you want to go to 1,000 threads on a single core, now it's very much similar to designing a single core with a large instruction window. And there's another downside here. If you're not like multi-core, these threads actually share the fetch engine. And your parallel performance is limited by the shared fetch bandwidth. Because you cannot fetch, you don't have many different I caches, instruction caches. You cannot fetch from these different instruction caches because you do not have them. It's shared across many threads. Now you can say that I'm going to partition the I cache and increase the fetch bandwidth, but now you're looking more like multi-core again, right? Basically, multi-core is a partitioned, multi-threaded machine. Okay. And with simultaneous multi-threading, there's one disadvantage, which is the extensive resource sharing at the pipeline level. These threads actually share the pipeline also. And this extensive resource sharing can reduce both single thread as well as parallel application performance, whereas multi-core partitions these threads and gets better performance. Okay, so one other alternative, but again, this is not orthogonal. Today, processors employ multi-threading as well, except to small scale levels, like 2 threads, maybe 4 threads per core. Yes?
But I can recall that it's like Oracle now had some type of Niagara type of processors which has 64 threads, I mean 128 threads.
We will get to that. They have 64 threads, but not on the same core. They have total 64 threads across 8 cores. So each core has still 8 threads or so. But we'll get to that. We'll cover Oracle Sun's processors. You can actually, this is a scalable approach. There have been processors like the Terra multi-threaded architecture, Burton Smith Terra, heterogeneous element processor. That's another fundamental paper. I'm happy to send it out. They had, at the time, 256 threads on a single pipeline. And the pipeline, I believe, was 8-stage pipeline. But what they did was cycle-by-cycle multi-threading. Their workload was such that you can have many threads, and you didn't care about the performance of a single thread. You can partition the workload, and you can switch to another thread every cycle. That way you can have lots of threads. If you do not care about single thread performance, it's a great way of designing a machine. I think it's beautiful. because you can make the pipeline simpler also, because you don't need to optimize for a single thread at all. You can design the pipeline just for multi-threaded performance, right? So it's easy to have a very, I'm not going to say it's easy. It's relatively easy to design a machine that has many, many threads. But if you want to get the performance of a single thread, that becomes it's not scalable. Okay, one other alternative. You can, instead of adding more cores, you can integrate more platform components on chip, right? Memory controllers, Ethernet controller, some crypto engines. I know, I/O controller, disk controller. You can imagine putting that on chip also. You can putting an entire system on a chip, right? In a general purpose machine. And this could be a viable approach going forward also. The upside of this is this speeds up many system functions, right? Network interface, Ethernet, memory, I/O, storage. The downside is, again, not all applications benefit, right? For example, if you have CPU-intensive code sections, multi-core gets performance with those, but you cannot get performance by adding all these components. And eventually you'll be limited, right? After you put the entire system on a chip, what else are you going to put on chip? Add more cores probably, right? Okay. And people have been doing that also, right? Memory controllers are on chip today. Ethernet controllers have been on chip on some of the server processors. Even crypto engines have been on chip on server processors like Sun's, Oracle's processors. But again, not all applications benefit. So this is not a perfect orthogonal alternative again. So this is a tougher one. Why not design a more scalable superscalar processor? Basically, this says design this much more intelligently. And the idea here is clustered superscalar processors, potentially with multi-threading employed in that also. Are you familiar with clustering, clustered superscalar? Yes? Somewhat. So the idea is, well, maybe I'll go through here a little bit quickly. So clustering has been employed actually in real designs, in alpha integer units, for example. Basically, you divide the scheduling window into pieces. Instead of searching the entire scheduling window, you divide it into pieces. And I'm giving the high-level idea. Implementation is very different. But you search only a portion of the instruction window to figure out which instructions are dependent. And if you actually put the dependent instructions into the right piece of the window, then you don't need to search the rest of the window. This makes a more scalable engine. And that's what Alpha 21264 did. This was one of the fastest machines of its time in 1990s. They basically clustered, instructions are steered into these different clusters. These are called clusters. And you can have cluster 0, 1, 2, 3 here. And these clusters can schedule instructions out of order. And within clusters, scheduling can be in order. So you can have in order scheduling here. So you don't even need to search. You just need to do FIFOs, FIFO queues. I guess I should stop writing on top of everything that I've already written. But you can basically design a machine that's much more scalable this way. It's still out of order execution. It's still trying to get high single thread performance. But basically, you have these FIFO queues for different execution units or different clusters. FIFO 0, 1, 2, 3, 4, 5, ... And you have some execution units here for each cluster. And even a partitioned register file. Register file 0, 1, 2, ... Now there's a steering unit that takes instructions as they come from a single thread and says, instruction, you go here, you go here, you go here, you go here. Not round robin, of course, but in a more intelligent manner. If you put your dependency chains into these FIFO queues, now it's beautiful, right? When this FIFO queue, when this instruction executes, hopefully the dependent instruction is at the head of the queue. Hopefully the next dependent is at the head of the queue. Now you can do FIFO scheduling here. These are all out of order with respect to each other, but in order within itself. Now this is much more simpler. There's no search associated with it, right? You just look at the queue. Is it ready? Is it not ready? Head of the queue. That's it. Now, so that's the beauty of it. So you don't, as long as you can minimize this communication between clusters, this works nicely. The upside is you have smaller scheduling windows, simpler algorithms to wake up instructions. In this case, the wake up is the top of the queue ready, head of the queue ready. You can have smaller ports into register files because these are partitioned also. You can have faster within cluster bypass. So you can bypass the values of dependent instructions, forward the values much faster instead of going to a different cluster. The downside, the big downside here is extra delay when instructions require cross-cluster communication. And you can imagine that this could happen, right? Now you have a load imbalance problem. This is, again, a parallel machine, right? If you look at this, you can have a load imbalance problem. What if everything is dependent on each other? What if many things are dependent? What if you don't have that many dependence chains? Now you can fill up this cluster. Once you fill up this cluster, you start putting the dependent instructions somewhere here. Now you need to wake up instructions in another cluster, right? How do you do that? If your dependencies are complex, the steering unit becomes the bottleneck. And that steering becomes hard. Okay, and this is one example basically. You can, scheduling within each cluster can be out of order also. It doesn't have to be in order as well. But it's still a much more scalable design of a machine. And this is what I've shown you here. You have these FIFOs that are replacing this hard to scale monolithic instruction window. And people have shown that these designs are actually much simpler. This is a simpler out of order execution design. And I guess I will not go into, and if you actually want to read more about it, we don't have time to cover all of this. This is a very good paper that introduced, that actually evaluated the idea of clustering. It's called complexity effective superscalar processors. And what they've shown is, and you can, this is just to show you the complexity of a single core design. What they've shown is you can actually have intercluster bypass like this that is not perfect, whereas you can have perfect bypass within a cluster that is simpler to scale. Okay, so let me go back to now that we've covered clustering a little bit, let's take a look at what are the advantages and disadvantages. So the advantages of this is simpler to design than superscalar machines because now you have these simple FIFOs, right? And again, even if they're out of order within a limit. And this can improve both single thread and parallel application performance also, right? What you can do is when you have a single thread, you use all of the FIFOs. When you have multiple different threads, you basically cluster. You separate the threads. You say thread 0 goes here, thread 1 goes here, thread 2 goes here, ... So you can have best of both worlds almost. The downside again is you get diminishing performance returns on a single thread. This clustering reduces performance because you cannot have perfect steering of instructions to these different clusters. You cannot get rid of that communication, that fine-grained communication between instructions. And if you're interested, you can take a look at that complexity effective superscalar processors paper. What they report is compared to a monolithic instruction window, they get a 20% performance loss with clustering. They can improve energy efficiency, but the performance loss is still very large. And parallel performance is still limited by shared fetch bandwidth, right? If you want to multi-thread this, you still share the fetch bandwidth steering unit. You can partition the steering unit, perhaps. Well, again, I will contradict myself, as you pointed out correctly. I said simpler to design than superscalar, but all of these things, if you want to improve performance and get it to the level of superscalar out-of-order machine with the same monolithic instruction window, it becomes difficult to design. And this was actually a very compelling competitor to multi-core at the time when people were thinking of what do we do next to improve single-thread performance. This was the biggest, most compelling competitor perhaps, because this is a much more scalable out-of-order engine. It was actually employed in some form in many processors today, except it's not scalable enough to be employed in full force, just like multi-core. Okay, one other alternative, which many people actually do not think of, interestingly. I would normally ask this question again. Maybe I should have asked, but it's too late now because the answer is on the board. One other alternative is traditional symmetric multiprocessors. Why are we even trying to exploit the transistors that are provided, right? Why not have smaller processors, simpler potentially processors, or maybe we have achieved some level of performance and energy. Let's keep that and keep stamping out these processors. It's just like these industries that are not making progress anymore. Maybe light bulbs, right? I don't want to denigrate the light bulbs. Maybe there's a lot of innovation that's happening there. But the traditional light bulb is the same, right? You basically have fixate on a design and you stamp it out. We can make our industry commodity like that. Now that has other implications than technical implications. That has economic implications also, and maybe job security implications also. But this is a reasonable alternative to consider, right? And actually it has some upsides. You have smaller die size, right? Especially when you're reducing the size of the technology node to almost 10 nanometer today and below 10 nanometer, faults are becoming much more prevalent. And if you have a smaller die size, perhaps you can tolerate those faults much better. Or you can reduce the vulnerability of the entire chip to the faults much better. And perhaps you can reduce, you can increase the productivity and increase the cost efficiency of designing a chip by having a smaller die size. Now there are a lot of things that go into this, and I will not be able to do justice by talking about all of them in 5 minutes. But this seems to be a very nice proposition. So why don't we do this? Like what is the advantage of multi-core over these traditional symmetric multiprocessors? Any thoughts? A traditional symmetric multiprocessor is basically a single-threaded processor. You have processor 0, processor 1 has its own die, and they somehow connected to each other. Some interconnect. That's right, communication, right? Now these processors communicate through the pins of chip communication, and that latency and bandwidth is very much limited, right? Well, I guess that's a different thing. Oh, there are other advantages too, looks like, to symmetric multiprocessing. First of all, if you have fewer shared resources, you can have many shared resources. And so if you, what I was thinking of is you can have private memories here. Yeah, if you have private memories, you don't need to share the memory bandwidth. That's right. But I think what you're getting at is what I had in mind here, which is you have now longer latencies between cores. Shared data access limit performance, and parallel application scalability is limited because of this.
It is over the same pin set.
Exactly, yeah. Basically, all of your communication, shared data access, is this processor needs to access a data that's written by this processor. Now you need to go off chip to do that communication. Whereas if you had these two processors on the same chip, core 0 and core 1, you could communicate through the shared cache. Or even if you communicate through the private caches, it's still much faster because the communication remains on chip. And that's the biggest downside. So with this traditional symmetric multiprocessor, you get smaller die size and fewer shared resources. Each processor can exploit its own resources, but the communication latency and communication bandwidth is much lower because you do off-chip communication instead of on-chip communication. And also, you can, because of this, again, the upside here can become downside here. You get worse resource efficiency because you get less sharing, right? You can have here, for example, a 2 megabyte cache, and you can make it private. You can have 2 megabyte cache here. If this core needs only 1 kilobyte, and if this core needs 3.9 megabytes, well, too bad. This core cannot access this 2 megabyte over here. It can. You can make it access it, but it's going to be very long latency, right? Whereas if these are on chip, you can share resources much more efficiently. You're not taking advantage of that. So this is likely not a good solution, even in terms of performance. If you want to solve larger problems, this solution is not a good solution. Okay, there are actually many other alternatives to multi-core. Yes.
Most probably it is much more low power than the multi-core one.
Again, if you want to solve larger problems, it's not clear, right? If you want to have a very large application and scale it out, this may consume a lot of power because of communication. Whereas communication on chip may be low power. It depends on the problem. I think if your program is mostly parallel, again, it could be lower power. If you can keep everything in its own chip, yes, it's probably low power. Yes?
We always talk about pure concepts, symmetrical multiprocessor, and loosely coupled, tightly coupled, and so on. But there are always in between. There's a spectrum, right?
That's it.
These are the two ends. So it depends on the degree of sharing, of course. So there are solutions in between, right? Not only local memories, you have different levels of shared memories as well, distributed shared memory architectures and so on. So.
That's right. I agree. I've been doing this as totally orthogonal alternatives, but these are not orthogonal also. You can actually today's systems are symmetric multiprocessors that consist of multi-cores, right? Each processor consists of a multi-core. And that's a reasonable approach to scale. But the extreme is, let's not put one more core on chip. What else do we do with it? Basically keep one core and keep the status quo, if you will. But you're right. That's all of these solutions are actually combined together. Okay, there are actually many other alternatives that people have considered to some degree. One is data flow, which is a fascinating topic. And data flow actually is implemented today in out-of-order processors internally without being exposed to the programmer. But I'm actually thinking of data flow explicitly, like explicit programming of data flow in computers. And that's actually a very scalable, potentially scalable way of actually improving performance. There are downsides to it. Like, how do you debug this if you expose it to the programmer? And that's one of the reasons why it didn't take off in the 70s and 80s. And even to the 90s. But this could be an alternative to examine potentially if you can figure out how to actually make it easy to program. Vector processors, SIMD, these are already available today in mass scale. You can actually program them in a much more easy way than SIMD. But again, that's not a perfect alternative to multicore because it's specialized. Integrating DRAM on chip is similar to integrating other resources, but this turns out to be a very tough problem. And we'll talk about this when we get to memory systems. Perhaps reconfigurable logic. Instead of having multiple cores, just put reconfigurable logic, right? This is an interesting approach, but it's probably not yet. It's not clear that it's general purpose today.
By the way, what do you think of 3D memory architectures? That is, the memory stacked on the chip itself.
So I think they're interesting. They're an interesting way of reducing the memory bandwidth and energy problem.
Automatically fed to the processor itself. So have you just seen the architecture from Georgia Tech University? That is, they have one memory layer over the processor, multi-core processor set. Have you seen that?
Yes, I've seen that. And I've seen people looking at similar designs also at different places.
So
Yeah.
it will most probably reduce this I/O bottleneck due to memory.
That's right, yes. It will reduce it, but it'll be a step function.
Yes.
So it won't be, like it won't get rid of the problem. It will help.
Or it will just, for example, when we see integrated DRAM on chip, then maybe we can think of seeing new, let's say, approaches in memory and chip coupling.
That's right, exactly, yeah. So those solutions will be employed to get rid of the shared resource bottlenecks as we go along. One downside is with 3D is the thermal issues that happen, like where does the heat go and how do you manage that heat is a very important, very interesting problem. So it's not clear if you can keep stacking lots of things.
Yes.
Yeah. Okay, so just a review, we've covered a lot of alternatives and some alternatives we did not cover as much because they're probably not as promising as these ones. But none of these, industry has moved to multicore because none of these alternatives proved to be that good. And multicore was a much easier, simpler way of improving performance as well, even though it involves a programmer, maybe more than a little bit. There actually, potentially your solution could come here. And this is actually a very interesting research, a hard research area, but an interesting research area. What other alternative models do we have to multicore? Maybe you can come up with a better way of designing more scalable superscalar out-of-order engines. And one of my students is actually looking into that, and he has some designs. But this is actually rethinking what else can we do instead of adding more cores is a very interesting research direction. I think that ties a little bit into, I thought this would happen earlier, but that ties a little bit into why computer architecture is interesting today, in my opinion. I think today is a very exciting time to study computer architecture. Like in the 90s, it was not so exciting because everybody was doing this, bigger, more powerful single core, which was not so interesting, right? Right now, the questions are not clear.
It was interesting at those times also because it was the first time that I met with the IEEE Spectrum on that alpha chip that you have mentioned.
Oh, alpha chip.
1991 April issue, and it was the first time I saw that, and I just thought that I have to study computer architecture. So it is not, again, compelling, okay?
That's right, yes. But it was perhaps not as broadly interesting. I was very excited about all of that also, and I'm still very excited about that, and I'll briefly talk about that too. But right now, everything is in a change. It was very difficult to design a non-traditional computer architecture, whereas today, it's easier because even industry doesn't really know what to do, I think, going forward. You had a question in the back? Yeah.
Do we consider assembly extensions to CPUs, like Intel's assembly extensions? Do you consider vector processing?
No, I don't consider those vector processes. They incorporate principles of SIMD, single instruction, multiple data, but they're just an instruction again. You can think of that as a hybrid. But an instruction operates on multiple data elements, and that principle is still there, but it's not a full-blown vector processor, whereas GPU is a full-blown vector processor. Because
Do they have separate registers specific to these specific instructions that they have come up with?
so the main difference is Intel's designs are not flexible. They have these instructions that are pre-specified, but you cannot do a whole lot of things. You cannot change the vector length as much, for example. So, you could consider at some level it's a vector. It incorporates the principles, but you still program it with a single-thread programming paradigm, right? We can discuss that. Those are more philosophical, I think. Okay, so I think, why is this exciting? Because industry is in a large paradigm shift. I think the alternatives we covered are actually showing that the paradigm is changing. The paradigm was this, bigger, more powerful single core. That's no more the paradigm. There are many different potential system designs that are possible, and the many difficult problems that are motivating and caused by the shift. And we're not going to talk about this again. We can define a lot of things: power and energy constraints, complexity of design, difficulties in technology scaling are pushing the industry to new technologies today. The memory wall and gap, reliability wall and issues, and programmability wall or problem. You could think of these walls and problems. These are all interacting in ways that the industry cannot figure out today. And that's exactly the reason looking into computer architecture and hardware-software interaction today is very important and very exciting, because if you come up with a new solution that solves some of these problems very well, you can actually affect the industry much more easily today, regardless of wherever you are, actually. So because there are no clear definitive answers to these problems. So if you look at computer architecture, these problems that we discussed briefly affect all parts of the computing stack if we do not change the way we design systems. I don't know why these are white, but they're actually blue here. They're white here.
The blue color is not defined.
And this you have to guess what that is. That's the homework assignment for today. I can see what it is here, but you cannot see what it is there. This is supposed to be red. But basically, all parts of the stack is affected by, for example, Mutlu multicore, right? Multicore basically changes the interface a little bit. Now the programmer cannot just write single-threaded programs, right? If you want to improve performance, right? If you don't want to improve performance, then you don't care about it anyway. You need to change the entire interface, and there's no clear definitive answer to that problem. Where do you solve the problem? Do you solve the problem at the programmer level? Well, that doesn't seem to work very well. Do you solve the problem at the microarchitecture level? That may not work very well also if you not have some support from the programmer. And we will discuss this when we talk about heterogeneity. Maybe the solution needs to be cooperative. Maybe you have some things at the microarchitecture level that exposes things to the programmer, and the programmer or the runtime system or the algorithm designer can tweak their designs a little bit and add hints to their program such that the microarchitecture can much better take advantage of the solution. So maybe the solution is not by adding more cores anymore, but adding more intelligence into the system such that the software can exploit it. Has anyone guessed what this is? User. That's right. It is the user, right? We often forget about this part. But we're actually designing systems for the user in the end. And that user is very important. And we're designing the software for the user. And if we cannot design the software very well anymore, then everything breaks. OK. I guess this is my last slide on philosophy of computer architecture. But if you're considering computer architecture, you can actually revolutionize the way computers are built because of this. But with one caveat, I think the caveat is it's not business as usual in the 90s before. In the 90s, you design a much more scalable core, right? But now you need to understand both the hardware and the software and change each accordingly. If you do changes to the hardware such that it makes life much harder for the programmer, then that's probably not a good change. And I view multicore as that way. It's a change that makes the hardware designer's job much easier, but the software designer's job horrible if they want to achieve high performance. So this is actually similar to one of the books, one of my favorite books. You can actually invent new paradigms for computation, communication, and storage. And this is a recommended book. You can do the reading tonight if you wish. But this is very, very heavy reading for tonight. This is Thomas Kuhn's structure of scientific revolutions. And I think computing industry is in the middle of a revolution because there's this large paradigm shift. He defines pre-paradigm science as no clear consensus in the field. And this is where we are today. Normal science's dominant theory is used to explain things, business as usual, basically, as I call it, and exceptions are considered anomalies. So it was normal science in the 1990s, or normal engineering. I think you can apply these concepts to engineering also. And revolutionary science's underlying assumptions are re-examined. So we should be re-examining these underlying assumptions today to actually fix the problems that we see. Because it's not normal science. We don't design single processors anymore. So dominant theory cannot be multicore. That would be my assumption here. Today, it may look like the dominant theory, but there's really no clear consensus in the field today. Okay, but first we need to understand the fundamentals, because you can change the world only if you understand it well enough, right? So let's take a look at some of these things. Basically, we'll take a look at some of the past and present dominant paradigms and their advantages and shortcomings. I think we actually looked at some of the past dominant paradigms. We've looked at their advantages and shortcomings. Now we're going to look into the future. Like what can we do to make things potentially better? And we'll study several things, some existing multi-core processors and heterogeneity for now, and cache design. I'm going very fast, I think, but is this reasonable pace? Reasonable pace? Yeah, okay.
Just a question, where does DSP processors fit in? I mean,
Oh.
are scalar processors and what's happening to those in the market?
So I think my discussion here is more general purpose market focused. Certainly DSP processors are an important, specialized market. And I think they have their place too, but they cannot solve all the problems in the world. And DSPs have actually been becoming more and more general purpose over time also, right? Now they have the VLIW architecture, and TI has been trying to get out of that space and make their processors more general purpose. So I think a lot of the things that we discuss here will be applicable to those, but we'll not focus on those. A lot of the basics will be applicable, the fundamentals will be applicable. Even DSP processors have gotten into multi-core also, right? That's
Some of the multi-core are trying to take business away from the DSP.
that's also
That's been the biggest kind of Intel versus TI kind of battles.
exactly, yeah. So I think specialization will always be there for applications where you get a lot of value out of specialization, and that's one of the reasons for going into heterogeneity. You can actually design some special things, special cores inside your architecture to get better performance, even in general purpose applications. So I think that trend will still stay there. You will still have some specialized portion to the signal processing, for example. But that won't be the dominant paradigm. That will be used when you have an application that matches that particular piece. Okay, let me know when I need to stop, okay?
Actually, you have to stop because just 1 hour is over.
Oh, is it just over?
Understand?
8 minutes. Oh, we have 8 minutes, so I can. Let me. 8 minutes? Okay.
Look,
7.
I thought that we just had started.
Yeah, we started a little bit late, I think. And we have many slides, actually. I think we're nowhere near done. But that's okay. So let's now delve into some of the multi-core designs that industry have followed. And this is a very old slide. I cannot keep up with the new cores, but it's not actually that old. It's just two years, perhaps. Basically, these are some of the multi-cores that we see today. Even NVIDIA Fermi, they call 448 cores, which I do not agree with, but they're really not cores, right? They're really a lane, execution lane. And you cannot operate it independently. If you cannot operate it independently, you cannot call it a core. But that's okay. That's their marketing strategy, perhaps. But we have all these machines with different number of cores, and some of them are heterogeneous, although not the kind of heterogeneity that I will exactly describe later on. What we really want with many cores on chip is n times the performance with n times the cores when we parallelize an application on n cores, right? Unfortunately, what we get today is Amdahl's law. That's the first thing, right? That's the serial bottleneck. So, and the second is the bottlenecks in the parallel portion. What is Amdahl's law? We've looked at this. I've changed this to F here, and I would again encourage you to read this paper. It's good bedtime reading. It's much better than Thomas Kuhn. Much more easier to follow. And we should not forget this. We'll get back to this. We have these different overheads: synchronization, load imbalance, and resource sharing in the parallel portion, and the serial portion, serial bottleneck. The problem is these serialized code sections. Many parallel programs cannot be parallelized completely, and there are many causes of this. These sequential portions, critical sections, barriers, and limiter stages. And I will describe these in a little bit more detail later on. These code sections reduce performance, limit scalability, and waste energy. And they can actually revert a lot of the benefits of this large-scale parallelism that we have on chip. So we'd like to somehow handle these at some level. One example that I had shown you earlier, when I visited, MySQL, even a parallel application like a database that gets lots of queries, each query first opens some database tables and then performs the operations on those tables, on those rows and columns of the databases that you keep open. Now, this portion is parallel, or mostly parallel. This portion turns out to be very serial because you need to access some open tables cache where a lot of different processors are operating on at the same time. It's only one example of a critical section in MySQL. MySQL is a database program. So this turns out to be protected by critical sections, and these are supposed to be red. I think I have a problem with the projector or one of the cables here. So whenever you see this dark black, it's really red. And this is supposed to be orange. That's the name of our research group. So if you look at MySQL, as you increase the number of threads that you add, as you increase the number of area that you devote, as you increase the number of cores, this is what happens to performance. Your performance peaks at some point, and then it gets reduced because of the communication overhead. Now the processors need to communicate the locks and share data with each other. That's what we have today. I'll show you some mechanisms that keep us in this curve. And that today we have this, and with asymmetric multi-core we can achieve something like this. And hopefully you can extend some of these going forward with much better mechanisms. But basically this comes, there are demands in different code sections. What we really want is, in a serialized code section, you perhaps want one powerful large core. If everybody is waiting for that thread, you would like to execute that thread on that one powerful large core. Whereas in a parallel code section, you really want many wimpy small cores, right? That you don't care about even how to design to be high performance. You just want to optimize that for very low power. These two obviously conflict with each other, right? If you have a single powerful core, you cannot have many cores. And a small core is much more energy and area efficient than a large core. You would like that also. Uh-oh. This may be a PowerPoint bug. And it is. So it'll be fixed hopefully now. There you go. This was not there before. Okay, so what are these large versus small cores? I will not go into detail. Small core can be in order, narrow fetch, shallow pipeline, simple or no branch predictor, few functional units. Large core is this large core that we've discussed here. And large cores are power inefficient. And this is a rule of thumb that has been developed at Intel, I think. Basically, for 4x the area, you can design a core that has 2x the performance. That's a square root law. But this doesn't always hold. If you go to 1,000 times area, probably square root of 1,000 doesn't hold. It's hard to get that performance. Performance usually grows slowly than area. But with small number of, with a small area, this seems to hold. And this is one paper that discusses some of these issues. This was by Ed Groshovsky, best of both latency and throughput. This is one example they had with large core versus small core. And this is the pipeline depth with normalized performance 5 to 8x here. Normalized power is 20 to 50x of the large core. And normalized energy per instruction is also high. So if you want to optimize for energy per instruction, perhaps in-order core is better here. So let's take a look at some of these small cores. This is a small core. And Sun Niagara, which you mentioned earlier, is one example of a small core. This was actually a 32-way multi-threaded Spark processor. This was one of the earlier multi-cores, although it's not the earliest. We'll see the earliest actually is the IBM, I think, dual-core engine that hit the market first. But if you look at this has Spark cores that are 4-way fine-grained multi-threaded, and you have 8 of them. That's how you get 32 threads. And they share some L2 caches, and they also have 4 DDR channels. This is an expensive piece of hardware because lots of channels, right, to be able to supply. And their design point was the server market, which could afford some of these processors at the time. Or not, because Sun is out of business today, right? That's but anyway, if you look at the core, it's very, very simple, right? This is the small core. It's in order. It has a 6-stage pipeline. It has dual issue, multiple instructions per cycle, but it's fine-grained multi-threaded. Basically, every cycle, you switch to a different thread. And you have 4 threads. Now, you don't need any branch prediction because by the time you fetch the next instruction from a thread, the previous branch is resolved. That's the beauty of fine-grained multi-threading. And they did not have branch prediction. They had a very simple core. So they were purely designed for throughput. They did not even have an FP unit per core. They had FP units shared across cores. Now we'll see that they reverted these design decisions going forward because they've hit the Amdahl's bottleneck in a single thread. And they had round-robin thread selection. When a thread actually went to miss in the cache, if all threads were missing in the cache, this core became idle, right? But if only one thread missed in the cache, now you had 3 threads to execute. Now you would be executing in an efficiency that's 75%, right? Because you'd be fetching from a thread every 3 cycles in a row, but that thread that missed in the cache, you wouldn't be fetching from it. That's the downside of fine-grained multi-threading. So this was actually designed for commercial applications, and because of that, they want a very highly multi-threaded engine. Because if you look at a commercial application, the instruction level parallelism they found is low, thread level parallelism is high, and these were mostly waiting for memory. And we'll see their design choices going forward in terms of how to improve the performance. So if you look at, again, this is from that paper. I'm not going to go into this in detail. But what they found is if you have a single issue processor, it would compute, it would have memory access, compute, long memory access, compute, long memory access. If you actually designed a larger core, as we discussed here, the performance would improve by little because it improves the performance of the compute portion, but it doesn't tolerate memory latency well. Whereas if you have a multi-threaded engine like this, four threads, you can tolerate the memory latency well. When one thread gets a cache miss, another thread would be doing computation. When that thread gets a cache miss, the other thread would be doing computation. When that thread gets a cache miss, a 4th thread would be doing computation. And you would only stall if you have all threads doing cache misses and you don't have any more threads left. But you can save a lot of time this way. So that was their main design goal. But they figured out that they actually need to improve the performance. There were actually applications that had computation bound, and there were better ways to tolerate memory latency. So they designed a larger core that never hit the market. This was called Sunrock. Actually, I skipped one thing here. They had the UltraSpark 2, Niagara 2, which actually got rid of the shared floating point unit. Now you had floating point unit per core. So that was a problem for them at the time. Should we stop?
It says 0.
0. Okay, if it says 0, let's stop, I think. Let's take a 5-minute break and we'll continue with this.